Facebook. Under his leadership, the team created one of the largest data processing and analytics platform in the world, a platform that made data accessible to analysts, engineers, and data scientists alike at Facebook. He's also the co-creator of Qubole Hive, you heard about Hive a lot, and served as the project's founding vice president at the ASF, Apache Software Foundation. He started his working career as an engineer at Oracle, where he contributed heavily to many core components of Oracle IDBMS and learned the art of building successful projects. Please join me in welcoming Ashish. While it's we do have the drawing for the free Stack Conference class. Winners Joe Boner from Data Networks. Or I will send you an email for the conference class, and we have a few books to give out. Well, they have the books to give out. I have Milind Joshi from Data. You pick your books there. Mahesh Gori Chen. There's no company name, it's Chen. Anatoly Fomenko from Congresssphere. And I have Igor Axinin from Altoros and Boris Coleman from Learn Computer. If you're interested, you can pick up your book at the entrance. Thank you.
What name did they announce right now? Because I've heard like a couple. It sounds like the name of my company. This is one. So where should I go? The front?
Alright, walk over here. Yeah, thank you. Hi folks, my name is Ashish, and I'm going to be telling you about some of the work that we've done in really making Hadoop work on the cloud at my company called Qubole. Has anybody heard about Qubole? Some, little bit. Okay, that's great. So let's start. I guess I was already introduced, so this is a little bit the same stats that Sqoop told you about, the same things. I did run the data infrastructure at Facebook for a long time, and I was also the co-creator of Hive there back in 2007, so I've been in the big data world for a very, very long time. So I'll start this discussion by telling you about a little bit about Qubole, and that's what sets up as to the work that we have done in cloud and live, sort of why we have done that work and what that work contains. So Qubole is essentially a really comprehensive cloud analytics platform. It's based on Hadoop and Hive, providing developers or companies a turnkey infrastructure, turnkey managed infrastructure, turnkey Hive infrastructure that they can start using without having to bother about setting that infrastructure themselves. We have spent a lot of time optimizing both these components for the cloud, and it of course works off of open data formats. And by open data formats, I mean these are same formats. These are formats, file formats that you can rewrite files on or see in text and so on and so forth. So our whole purpose there is let's work off open data formats. Let's be on the cloud and let's create this turnkey infrastructure which anybody can come and use without having to go through the rigors of installing a big data stack. And it's really catered towards applications around exploring data and applications around creating data pipelines and transformations. Really batch-oriented applications and applications in which you want to do some analysis, ad hoc analysis, and then convert that ad hoc analysis into more batch-oriented reports or batch-oriented data pipelines. So that's a bit about Qubole. And the reason that we have basically done this on the cloud is primarily to solve an inherent bottleneck that we see in a lot of companies today. And the bottleneck being that while on one side, a lot of companies have a directed trove of data, and on the other side, have these end users who want to use these data sets in various different ways. These end users are kind of dependent upon either infrastructure engineers putting together a stack, a big data stack in-house for them. And even after that, they are kind of dependent upon advanced data users to really munch data and create insights. So Qubole is trying to solve that bottleneck by providing this in the cloud. Going further, the service comprises of a bunch of components. The two main ones are, this is completely runs on EC2 and S3. And on top of that, we've taken the big data stack and truly made it elastic, robust, and fast. And this will be what we'll be talking about today. The red box is where I'll be focusing most of the conversations today. And on top of that, we have provided easy to use exploration applications and scaling applications. So that an end user who is not, or a data scientist or data user who is not very proficient with the big data stack can still make use of it. And of course, we augment this with a bunch of connectors so you can bring data into the platform. So that's just the overview of the platform. What we'll be focusing today on is the red box and some of the work that we have done there to make Hadoop and Hive elastic, robust, and fast in a cloud environment. And by cloud, I mean all this is running on Amazon, all this is running using S3 as a persistent store, and EC2 for getting compute loads. So let's just dive into it. So the first thesis is that there's a difference between the cloud and between bare metal. Running Hadoop and on bare metal is different than actually running in the cloud. It's not as simple as let's take an open source distribution and start running this on the cloud. There are certain fundamental differences. And the three that typically come to mind are, first, in a cloud environment, you can do dynamic provisioning of nodes, which you don't have in bare metal. Like, you either run out of cluster space in case of a bare metal deployment. You run out of clusters, then you go to your operations team or provisioning team, and they put in these clusters, they order them, it takes like a couple of months, and you kind of grow your cluster. Or if you're a big company, you have that entire supply chain kind of worked out, and you kind of expand that. On the cloud, you have the advantage of doing this dynamically and on demand, and I'll tell you what are the implications of that. The second thing is, while we talk about Hadoop as storage and compute together, on the cloud it's actually separate. S3 is separate from compute, which is EC2. So it is different from just having storage and compute together. It's sort of going back to the old world where you have storage arrays which you would scale differently from your compute clusters. And the third thing is, on the cloud, you have the ability to pick your price to purchase this data. So you have mechanics of people you can do optimizations in terms machine at what price, and you can really play around with that. So these are the three dimensions that I'll be kind of discussing in terms of differences between cloud and data and what the implications are there on the stack. So first let's start to dynamic provisioning. So what does dynamic provisioning lead to? So the big advantage of dynamic provisioning is transient clusters. You don't need to have if you're doing this in-house, you always have to have a dedicated set of machines. Always your capacity of the cluster is to the peak capacity. On the cloud, since the dynamic provisioning, your capacity can expand and shrink with usage. You don't always need to have hundreds or thousands of nodes running. You can go from 0 to 100 to thousands very easily. But that ability itself puts a burden on the user. Because even with this dynamic provisioning, with the ability of the dynamic provisioning, an end user, like a data user, still has to figure out, hey, if I'm running this workload, how big of a cluster do I need? What kind of nodes should I put into this cluster? So while there is an advantage that you can do some really smart things on the cloud with respect to your cluster sizes, the disadvantage is that you have, in the state of the art, like before what Qubole has done, in the state of the art, all that smartness has to come from an operator who's kind of doing this cluster management. So in Qubole, we kind of focused on this problem and we basically made Hadoop auto-scale. So there's no operator intervention. And essentially the clusters grow and shrink completely on demand, adapting to the workloads that are being put by end users onto the service itself. And that's a very powerful thing. It brings the advantage of the cloud and at the same time takes away the disadvantage of putting this burden on the end users in terms of how they scale the clusters. So what is the hard thing here in doing auto scaling? There are two particular elements which are hard. One, analytics workloads are typically bursty. It's not like a OLTP kind of a workload where you have high predictability of what your application is telling your OLTP clusters. Analytics workloads are bursty. Ad hoc queries come. Person might run it in the middle of the night, or person might run it during the daytime. So burstiness makes prediction that much harder. You can't just figure out how much of a cluster you need by simply looking at what is the current state. You have to add the prediction logic there to predict what it will look like, say a few minutes from now, 5 minutes from now, 10 minutes from now. So that is one thing that is hard about auto scaling on Hadoop. The second thing is while auto scaling is easy for stateless services, Hadoop, because of the HDFS, is stateful. So when you are growing nodes or shrinking nodes, especially when you're shrinking nodes, you have to be extra careful. While you just don't lock out the nodes which have all the three replicas of the data set, and then you are at a place where your data set is kind of elaborated. So those are the two challenges. And the way we have solved this in Qubole, in making Hadoop truly auto-scaled, is by following a problem. This is what we do. All the task trackers report their bounce time to the job tracker, and the job tracker continuously computes the time it is required to finish the existing workloads. So it looks at the existing workloads, it has some other inputs that it gets in terms of what has happened in the past, and on the basis of that, it tries to compute the amount of time it is required to finish the existing workloads. Now, if this time is greater than a certain threshold, it starts adding nodes. It uses, just starts adding nodes to this cluster. At the same time, if this, if there's insufficient work, if it finds insufficient work, it starts decommissioning the nodes but at hourly boundaries. Because if you're familiar with EC2, once you buy a node, you get paid for an hour. So hey, let's just keep that node for an hour because you're going to get paid for it. If any future query comes in or a future workload comes in, you can still use that compute. So that's what it does. It removes the node at hourly boundary if there's insufficient work. However, there are certain restrictions that it applies by deleting these nodes. One restriction is for current jobs, if a node has the task outputs of a current job, of a job that is not completed, then it will not take that node down. So that smart is kind of built into the system. It does fast decommissioning of data nodes, and we can do fast decommissioning primarily because the way we are using HDFS in our setting is not as a full-blown persistent store. Our persistent store is S3. We use HDFS as a cache. So we can quickly take down those data nodes without having to worry a lot about, hey, what are we doing with the replicas, and without having to completely replicate everything before taking down the data nodes. We absolutely have to make sure that the task outputs for the current jobs, if they are there on the node, then we can't take them down. That's from the task pattern. And on the data node, we do fast decommissioning. And at the same time, we give some inputs or we give some parameters to the users where they can say, okay, don't go below 5 nodes. There is a minimum that we can do. So within those restrictions, we delete nodes at hourly boundaries if the workload goes. So that is some of the smarts that have been built in the auto-scaling part of the work that we have done at Qubole. There's a blog post about it at our blog. Feel free to check it out. There's a whole bunch of blog posts about all the stuff that I'm talking about here, there as well. So let's come to the second dimension. Let's explore the second dimension of how the cloud is separate or different from their method. So compute and storage on the cloud are separate. And why is it that way? Primarily because you don't want, so compute is more expensive on the cloud than storage. And if you have to keep your compute up in order to, so suppose you could say, I'll just run my Hadoop cluster and put everything in HDFS and use that storage cluster. If you take that model, then you start paying for the compute while you're not using it. And it's much cheaper to just use S3 because there you're just using storage, you're not paying the cost of the CPU, and it's just more efficient on your budget. So as I said, it has kind of evolved in a place where you have S3 for storage and EC for compute, and they are separate, they are not clubbed together. However, this separation causes both slowness as well as variability in performance. Since from a compute node you are accessing S3, you get a lot of variance in terms of the latencies. When you're doing any file operation from S3, you get a lot of variance in the latencies. And that leads to variability in your workflows and also the slowness as well. So in order to mitigate that, we have done a couple of things that we do. We have implemented a caching file system on top of HDFS so that when you first encounter a query, a query first encounters a certain data set, we cache out that data set into HDFS from S3. So subsequent queries can go to that data set. And we have done some smart tests in the cache as well. And the second thing that we have done is we have done some work to mask out S3 latency by using techniques like pipelined file access and so on and so forth. I'll go into those in a bit. So in terms of caching, this is how kind of caching works. When you execute a workload, the map task reads the data from S3 through the HDFS file system. And then as it is using the data to process the query, at the same time, it is in parallel or it is asynchronously writing the data out to HDFS as well as S3, to the HDFS cache as well as a representation of the cache in S3. But it is doing that in a columnar manner. So it takes this data, this open data formats, again, it's like text files and so on and so forth, and on the fly it's converting it into column-oriented storage, both in HDFS and stores that on S3 as well. So that gives you two benefits. Of course, the cache itself gives you, the HDFS cache itself gives you benefits right away because you have kind of the variability of S3 goes away for subsequent queries. And since it's a columnar cache, you get this added benefit that for analytics workloads, if many of the tables are very, very wide, and if you're looking for very, very small number of columns, which is where most of the queries fall, those queries get a lot of speed up. So this is what we try to build in terms of caching. And this is done all transparently to the user. The cache gets invalidated, the data is written, all the lifecycle management of the cache is kind of implemented there, and it was very valuable. So the other benefit of, so apart from masking the performance degradation with S3, the other big benefit of this is the cache allows you to work with open data formats, which are mostly row-oriented, without having to sacrifice too much of the performance that comes with those kind of formats, primarily because of its columnar nature. So the other thing that we have done is masking S3 latencies. The other place where S3 latencies hit you is when you are doing any kind of file operations on S3. So the two places where this is done fairly often is in spread generation. You go and look at file metadata, you want file metadata all the time. And the second place that is done is when you're doing file reads, you have to first open the file and so on and so forth. Both the file opens as well as retrieving the metadata for files are slow operations in S3. There's, of course, SDFS, if you're so, people know that there are a lot of files in a particular data set, SDFS has an overhead when you are doing spread generation. Now that is multiplied by a factor when you go to S3. So it really bogs down. If you're running these workloads on data sets with a lot of files, it really bogs you down. So for that, we have implemented, we changed the spread generation algorithm from being a very seek-oriented algorithm. It goes and for every file it fetches the metadata to a more bulk-oriented algorithm. And for file opens, we can also optimize by making them pipeline. So for spread generation, instead of getting metadata per file, we get the entire metadata of a particular directory, all the files in one go, and then we merge and eliminate those files that are not needed by the particular transformation of the query. And that leads to a significant amount of speed up. Like this is a benchmark done on a very simple set count start and query. And as your number of files increase, which is quite often the case because people are putting data into the cloud in small batches every 5 minutes, and each of those files is generating a lot of small files. The performance improvement is quite dramatic, 8x in some cases as well. On the pipeline tokens, what we do is actually it should be called pre-open in the sense that even before we go and read the files, separately we kind of open them up and keep the file handles on, so that by the time you come and read it, those file handles are already there and you can start reading them. So we've done those kind of optimizations as well. And in some simple queries, you can see about 30% improvement on the workloads on S3. So last, let me talk about the things that you can do in terms of purchasing instances. So on the cloud, you have this beautiful model where you can get things on demand and you can pay on demand. So it's pay as you go kind of a model. But even in the pay as you go kind of model, there are a couple of variations. For example, Amazon has on-demand prices, and you can also buy the instances on the spot market. And the advantage of buying on the spot market is you get typically in usual workloads 50 to 60% discount on the price. But the problem there is that there is no, these are spot instances and they can be taken away from you at any time. Literally any time. But if somebody has a better bid, this spot node can just go away. So when you have a cluster which has a mixture of these on-demand and spot instances, and you take away these spot instances, it's really bad, right? I mean, if your mapper is, MapReduce class is running and you take away spot instance, all the mappers and reducers on that particular node fail, and you have to restart that. So that is one part of the badness. The other part is SDFS itself is disastrous there. Like suppose you take, if you have the 3 block replicas and all those 3 are spot instances and go ahead, you're kind of close because you're kind of your data is gone. So we have kind of addressed both of those to a degree with the work that we have done, integrating Spot, the Spot building with Hadoop clusters. We first of all provided very simple interfaces for the users to be able to have a Spot building strategy where they can say, okay, a percentage of my cluster, say 20% of my cluster can be Spot instances. I don't want to wait for more than 2 minutes when I'm bidding for Spot instances, so they can trade off between waiting for a longer time for their clusters to be up or react on the Spot market if they lose the nodes, to running at a higher budget with lesser number of Spot instances. And they can also configure the bid price, saying this is my bid price. If you can get the node in this bid price within that time of interval, so be it. If not, then just go with the on-demand prices and so on. So that's the feature that we have done. And on the HDFS side, we specifically to solve the problem of Spot instances being taken away at any time, we ensure that there's a replica of a block which resides on the on-demand instance. So we kind of changed the block placement policy there, so that when the blocks are being, when the file is being generated and this block is being placed, we absolutely make sure that one replica is there on an on-demand pricing. And that significantly cuts down the problems that you have with Spot instances. Note that this is still, caching usage of HDFS, so if something catastrophic happens and you use the on-demand node along with the Spot nodes, you still have a recourse of getting that data out back from S3. This has better characteristics in terms of recovering from Spot nodes going away than the vanilla block placement policy. So with that I kind of conclude. I want to stress one point. Cloud is different from running in bare metal, and it is different enough that you need to do certain specific things in order to make this stack work on the cloud. You have done a lot of that work at Qubole, and do check it out. Check the work that we have done. We blog about it quite regularly, and do check it out on our blog. And with that, I'll kind of conclude. Our service is open. You can sign up for free service for a certain number of compute hours at api.qubole.com/users/sign-in. And of course, we are always looking for great people to join our team. So if you are interested, absolutely ping us at our career stage and take it from there. With that, I'll conclude and open to any questions. Yeah.
Good talk as always you do. The processor architecture, processor computer cache, etc. is this architecture. The servers are cheap. It's over time. Secondly, in data centers, it's not always that the storage is removed in a block compared to the processor or server architecture. And there are multiple configurations being tried out in different data center environments. How are you going to continuously adapt and change on a regular basis? Yourselves helping other people.
So right now we are primarily on the cloud. So there the boundaries are very, very clear in terms of separation.
There are multiple architectures happening. You may not be familiar with this there.
Sure. So there are multiple architectures happening, but in terms of the API that we get at our level, there the distinction is there. Now if you go inside the data center, you have much more control, right? There you have more control. There's a storage cluster here and there's a compute cluster here and so on and so forth. Our caching work is applicable there as well. But we are not kind of, catering to that market as such. But the typical way that you do, storage hierarchies happen there all the time. And the way you mask out storage hierarchies is by putting caches at various levels to, mask out the storage hierarchies. You are also getting this, super expansion of cores in the CPU itself. And, that's a great trend. I think the data is still growing fast enough that everything cannot fit on a single machine. So I think there is still room for this kind of a thing. But the caching one is certainly applicable to storage varieties within the data center, except that we are not just focused on that now.
So what's your ratio to the caching and S3? Is it the same?
In terms of the size, you can configure it. You can totally configure it. So you can say, I want to keep like, whatever, 2500 gigabytes or terabyte of cache, as opposed to, so you can configure it. And typically what we see in data sets, it's usually the 10% of that data set is super hard. That is the last week or the last 10 days of data, which is like super hard, and the older one is cold. But you as a user can configure it saying that, my hot set fits in. I have like maybe 10 terabytes of data, but my hot set fits in 1 terabyte. So keep my cache to be 1 terabyte. And that will be the cache on S3 itself. The SDFS cache size kind of change with the size of the cluster. So if you want 1 terabyte of cache in SDFS, then you have to have certain number of minimum nodes in the cluster, so when the cluster brings up, comes up, it has about 1 terabyte storage. This is like not really. But typically, in my past experience, I've seen the hot set to be about 10% of the total set of the data, but there are applications you can kind of change that if it doesn't fit.
Yeah, thanks. Another quick question was, since your model is on the cloud, how do you, one of the things of doing in-house computing versus using the cloud is moving the data into the cloud.
Okay.
So what are your experiences there? How do people achieve moving large amounts of data
Into the cloud? So that's a good question. We today cater to data sets which are created in the cloud. So today we go to companies who are already running the services in EC2 and generating data already there in the cloud itself. You are also looking at connectors which enable you to move data out from your on-prem data centers to the cloud. Typically, the demonstrations there are twofold. Sometimes there's a bandwidth thing which can be worked out. You can always have a mechanism where you have different. Amazon has this thing for moving data into S3. You can actually shape this to see it. And then you can have an incremental load, which is not, it doesn't need that much bandwidth. So typically the bandwidth argument hits really the first part of it, and then the later part is easier. We haven't gone to that extent yet. Right now we are very focused on cloud data sets, which are generated in the cloud, or there are cloud services in the cloud itself, on which we can serve out the data. And also bear in mind that many people don't have the same scale of data as Yahoo or Facebook. On the cloud, probably 10 terabytes is huge. It's a big data set in the medium type of market. So on those ranges, the bandwidth argument doesn't arise that much. The bigger argument that arises is organizations being mentally prepared to put their data on the cloud. There is this perception that the security in the cloud is less. But then my question to most people is, do you trust keeping cache at home or cache in the bank? It's the same argument with data centers. You trust your own data centers. Like for companies like Yahoo and Facebook, it's a different argument. But for most mid-market companies, you don't know what is happening in your own data centers. Whereas people like Amazon are actually running industrial-grade data centers with a lot of compliance and a lot of checksums, checks and balances to make sure the wrong people don't get into the data center. Typically, that's the way data leaks. And even in terms of hardening and hacking and getting through into a data center, I think those are much better. In fact, there was some CIA report which actually alluded to that. But that's a percentage thing. So that is the other thing which, and we are kind of saying that progressively the market will move to this new paradigm where this perception we can fix and we will move to the cloud. But today, we are more focused on data sets which are being generated in the cloud and on companies who are easily able to move their data to the cloud, whether it is whether they're compatible with the security and whether they're compatible with the language.
I would assume that if I were to compare this with Amazon's own Elastic MapReduce, you're definitely offering things that you don't get in Elastic MapReduce in your service. So I would also imagine this is slightly more expensive than just running native Elastic MapReduce.
So we are actually in the base platform, we are going to price at the same price range as Elastic MapReduce. Our model is we are trying to do kinds of model. One is the same hourly billing and have the same rate as what EMR is. Or a subscription billing is says these many compute hours you get for this price per month. But it's going to be very, very competitive with Elastic MapReduce for the base platform. On top of that, the applications that we are building, whether there is an exploration app and so on, those will be priced separately.
So given that, is there any reason why anyone should use Elastic MapReduce?
No. I mean, there is one reason that they have a space, you don't have a space. So if you're, other than that, there's no reason.
We're out of time, so I want to thank Ashish.
Thank you very much.
And that wraps up our session today. We'll meet again next month, third Wednesday. I think it's February 20th. I want to thank all of you for coming.
Thanks so much.
No, still Alpha. But another team, global business, not the
Which is to say, the company is prepared to pay for it, which is to